Hello. In the previous part, we have seen analysis of cantilever beam using SolidWorks.
Now let us see another example. Say we have a truss like this and it is expected to be modeled with 40 millimeter square tube. The load distribution is like this. How we can do this? Here it has got hinge joint here. Here it has got a roller support and forces 2000 Newton and 3000 Newton are acting on these nodes. How we will do it with SolidWorks? By using SolidWorks environment, I have developed this particular line. So these dimensions are designed based on the given dimensions. The initial modeling is over. You are exiting the sketch. As we had done in the previous case, go for weldment. There you choose structural member. What kind of structural member? Square tube 40 by 40. So we use this. Select the members one by one in a particular sequence. It will be better. A sequence like this, like this, like this. So once you start clicking on the other line, it may show that it is not selected even if I am clicking it there. Sir, you go for new group, this option. Click new group. Then you click over here and click over here. So that way the cross section is completed. You click tick. So that's how the modeling of the frame is completed. Now we have to apply the boundary conditions like the joint features, degrees of freedom at the joints, and the forces acting on joints. Now let us first fix this. For that, you come for simulation, go for study. We choose static problem. You choose it, select. You have to first apply the material. Let us choose the material, alloy steel, linear elastic property, and you select the units. We verify the elastic modulus and all what are available for the material. Apply the material property for the model so that the model becomes this material and close it. Now go for fixture advisor.
Select
Fixture, fixed geometry, where you have to go for advanced reference geometry. That means here in a hinge joint, you have to apply how many degrees of freedom for this. For a hinge joint, there is rotation possible in this direction. That is about Z axis, there is rotation, but there is no movement in X, Y or Z axis, and there is no rotation about X and Y axis. So we leave the displacement all in zero condition. So here it is 0, this is 0, this is 0, and along that is also 0. And rotation along this X, Y, there is no rotation here, but along the perpendicular axis there is rotation, so we are leaving it. And you choose the section and select it. Thus you have applied these conditions. Along the plane there is no movement, along the vertical plane there is no movement, but perpendicular to the axis of the plane there is movement possible.
to apply the condition at a node.
Choose a reference plane. With reference to the plane, along the plane there is no motion. Along perpendicular to the plane, this direction there is no motion. Perpendicular plane also there is no motion. But being hinge joint, it is modeled by showing that along Z plane, that is in this direction, there is movement, but whereas no movement possible about X and Y axis. So thus you have modeled that joint. Similarly, go for this joint. You have to again go for fixture geometry. Use a reference geometry here. This is a reference geometry. Select the joint. This is a joint. And reference plane. Let us choose this as a reference plane. Now, being a roller joint, it will have movement possible in this direction. That is, along X there is movement. So we are leaving it free. And there is rotation possible about this Z axis also. So that is also left free. All other movements are fixed as 0. So along x-axis along the axis there is movement, vertical axis there is no movement, and a perpendicular axis there is no movement. And rotation along the axis no movement, perpendicular to the axis in this plane there is no movement, but perpendicular to the axis there can be movement, so we are not touching it. So we are leaving the movement along the x-axis free and rotation about z-axis also free. That's how we model the roller joint. Now go for force. Now we had to apply force over here and here. So go for external loads, select force. Where you have to apply force, you are applying force on the joint. Which joint? This joint as well as this joint. Okay. Let us consider that both forces are same. So we need to again give a reference surface. So, and the force is acting in the direction of surface, that is in this direction. And what is the force we want? It is say 2000 Newton. If this is the direction, it's okay. Thus, our modeling is complete. Now go for meshing, create mesh, run this study. So this is the result we get. We need displacement in this vertical direction. So choose displacement along the z-axis. So that's the parameter we want. If you want more results, you can click on the right hand side and you can add whatever things like factor of safety or stress plot, whatever. So if you double click on this, you get the stress plot. What is the maximum yield strength? 6.204. What is the maximum one developed? 4.7. It's acceptable. Now displacement in the z direction, click on this. What is the maximum displacement? 1 into 10 raised to minus 6. So here we have another option of undeformed shape. Okay. And if you want deformed shape, you can get it. Okay. Similarly, if you want to get a result like force, so choose the probe and you click on the point, say this point. So it will give you what is the value of the displacement over here. If you click over here, you will get the value of displacement over here. That means when you get a result by using this probe, you can get the values at this point, any point in the structure. That is how we conduct the analysis for this. Only thing is, after modeling, come to simulation, choose the study, then apply material, then apply the fixtures, then loads you have to apply, then go for running the study. You get the result. After getting the result, you can check different kinds of results, and what result you have to get, that you can define over here. So that's how the final analysis is performed using SolidWorks. Thank you so much.